Hello, we are presenting our heat transfer project on cooling rates of welding. Here's a little background and history about our project. In welding industry, cooling rates of a weld are used to determine the resulting crystalline structure of the steel. In industry, the cooling rate at 540 degrees Celsius is typically used to make those predictions. If a weld or metal cools too quickly, then martensite forms and causes the weld to be too brittle and can cause failure. Brother Orm from the Welding Engineering Department at BYU Idaho has asked us to develop a variety of cooling rate models that he can use to give his students the tools to become exceptional welding engineers. For our first model, we chose to find a model for a weld over a flat plate. There is a lot of graduate level research that has already been done on the subject of welding cooling rates. We took the opportunity to build on Sheng and Chen's work. Thanks to Sheng and Chen, we obtained a two-dimensional model that finds the temperature of a weld. It is a complex model that involves a Bessel function and an exponential integral function that took some time to learn how to calculate. Cooling rate can be expressed as the derivative of temperature with respect to time. In order to obtain an equation for cooling rate, we first needed to modify our model to be a function of temperature. We did this by substituting velocity with the change in distance over the change in time. After entering in all our parameters, the result is this expression and this graph. You'll notice in our expression that there are components of both an exponential function and a power function. This is important to note because when trying to do a curve fit from our measured data later, this shows we cannot simply use a power law or curve fit or an exponential curve fit to derive a similar expression as our model. When we take the derivative of our function with respect to time, the result is the cooling rate as a function of time. To find the time at which we need to look at to observe the desired cooling rate, we found the time at which 540 degrees Celsius was reached, which in this case was 9.52 seconds. We then use that time and put it into our cooling rate function to obtain a cooling rate of minus 507 Kelvin per second, or degrees Celsius per second. We then wanted to compare the cooling rate of our model with the cooling rate of our measured data, as shown in this graph. Since we could not obtain an accurate curve fit with simple curve fits, we approximated our cooling rate by finding the slope between two data points, that of the temperature at 540 degrees Celsius and the very next data point, which was given at 470 degrees Celsius. This gave a cooling rate of about minus 70 degrees Celsius per second, which is conservative as the actual cooling rate at that point would be slightly higher. This was found to be a better method to obtain an approximated cooling rate since the exponential and power law curve fits gave cooling rates around minus 45 degrees Celsius per second. When comparing the cooling rates between our model and the measured data, we can see that there is a significant amount of difference between what we obtained with our model and what we obtained with our measured data. This variation could be explained by data that was not captured fast enough. For example, our thermocouple only took data every 1 second. Taking data in smaller increments could show behavior that resembles our model a little bit closer. Another reason for this variation could be that our model is not yet fully refined and needs to be further examined. The behavior between the measured data and the model, however, were still very similar. They both behaved as exponential and power functions. In order to develop an accurate model, it is recommended that another look at the model be taken to determine why the slope was so high. An effort to obtain a model that levels off a little bit slower is recommended, much like the red dotted line that is shown there. One possible way to obtain a model that cools slower is to take another look at some of our other parameters that could be functions of time. Zeta sub x, for example, is calculated by taking the time it takes to travel big X amount of distance and subtracting that by velocity times time. The magnitude of the heat affected zone as well on the right hand side is a function of zeta sub x, which has time in it. Replacing these terms with equivalent expressions that include time could give different results.